Let me show you something weird. Almost suspiciously weird. I take a simple spinning top, place it on the table, and just let it go. No spin, nothing fancy. What happens? It falls instantly. No drama, just flop. Exactly what you'd expect. Gravity does its job, end of story. Now I do the same thing again, but this time I give it a good spin first. Not crazy, just a nice smooth spin. I place it down, and suddenly it stands there. Calm. Balanced. Almost like it forgot gravity even exists. It doesn't fall. It just stays up, spinning like it has some secret deal with the universe. And here's the part that should bother you a little. Nothing actually changed. Same top, same table, same gravity. So why did one fall instantly and the other just refuse to? Most people think they know the answer. Something about force, or spinning, pushing it up, or maybe some invisible support. Sounds reasonable, right? Yeah, it's also completely wrong. What's really happening here is much stranger and honestly, way more beautiful than anything you'd guess at first. And once you see it, you won't be able to look at spinning objects the same way again. I am Richard Feynman, and this is Feynman Rebirth. Let's figure out what's actually going on. All right, let's slow this down and really look at it carefully, because this is where the mystery begins. Imagine you have a simple spinning top sitting on your table. Nothing fancy, just a small toy. You place it upright and let go without spinning it. What happens? Of course it falls immediately. No surprise there. It tips over like it has somewhere better to be. Gravity pulls it down, and that's the end of the story. Now try the exact same thing again, but this time give it a nice steady spin before you release it. Suddenly, something strange happens. The same top, on the same table, under the same gravity, just stands there. Not for a split second, but for several seconds. Maybe even longer if it's spinning well. It looks calm, balanced, almost confident, like it knows something you don't. And here's where it gets interesting. Nothing about the situation has changed except one thing. It's spinning. Gravity didn't take a break. The table didn't become magical. So why does spinning completely change the outcome? Why does one version fall instantly while the other somehow refuses to? Most people jump to a quick answer here. They say something like, spinning creates a force that holds it up. Sounds nice, sounds logical, but it's not actually true. And once you realize why, you'll see that what's really happening is far more surprising and honestly, a lot more beautiful than that simple explanation. Now, before we go any further, we need to clear out a couple of very popular ideas that sound smart, but quietly lead you in the wrong direction. The first one is the classic. Spinning creates an upward force that holds the top up. It feels right, doesn't it? Like the motion somehow generates lift. But here's the problem. There is no such upward force. None at all. If you place that spinning top on a weighing scale, it will show the exact same weight whether it's spinning or not. Gravity hasn't weakened, and nothing new is pushing it upward. So whatever is keeping it up, it's definitely not a hidden force fighting gravity. Then comes the second idea. It's centrifugal force. You've probably felt this on a merry-go-round, or when a washing machine spins your clothes you feel pushed outward. So it's tempting to think that this outward push somehow stabilizes the top. But look closely. That force pushes things sideways, away from the center, not upward. And gravity? It pulls straight down. Those two directions don't cancel each other out. It's like trying to stop a book from falling off a table by pushing it sideways. You're just changing where it falls, not preventing the fall itself. Take a washing machine as a real-life example. When it spins, the clothes are pressed against the walls, not lifted upward. Or think about a fast merry-go-round. You feel pulled outward, not lifted into the air like gravity suddenly stopped working. The same idea applies here. Spinning changes motion, yes, but it doesn't magically create a new force to hold things up. So here's the key point. Nothing new has entered the picture. The same old forces are still there, gravity pulling down, the surface pushing up. Physics hasn't changed its rules. And yet, the behavior is completely different. That's your clue. The answer isn't about adding a new force. It's about understanding how motion itself changes the way those forces play out. So now let's pause and ask a simple question that almost nobody thinks about properly. What does it actually mean for something to fall over? Because we usually imagine falling as something just going downward, but that's not really what's happening here. Take a pencil and try this yourself. Stand it upright on a table and let go. Watch carefully. Does it just drop straight down? No. The bottom part stays almost in the same place, touching the table, while the top swings outward and downward. The pencil doesn't slide. It rotates. It pivots around its base. That's what falling over really is. Not just falling down, but rotating around a fixed point. Now the next question becomes more interesting. What causes that rotation? Yes, gravity is involved, but not in the way you might think. Gravity pulls on the center of the pencil, which is somewhere in the middle, not at the bottom where it touches the table. Because that pull happens at a distance from the pivot point, it creates a twisting effect. In physics, we call this twisting influence torque. Torque is just a fancy word for something you already understand intuitively. Think about opening a door. If you push the door right next to the hinge, it barely moves and feels heavy. But if you push at the handle far from the hinge, the same push suddenly works easily. Why? Because the farther you are from the pivot point, the more turning effect, more torque you create. Same force, completely different result. So when a pencil falls, it's not just gravity pulling it down, it's gravity creating torque, a twist that makes the pencil rotate and tip over. And once that rotation starts, it speeds up until the pencil hits the table. Simple, clean, no mystery. But now comes the real question. If falling over is just rotation caused by torque, then why doesn't the spinning top rotate and fall the same way? Because the torque is still there. Gravity hasn't gone anywhere. So why doesn't the same rotation happen? That's where things start to get really interesting. At this point, it's really important to separate two ideas that often get mixed up: force and torque. They sound similar, but they behave very differently. A force pushes or pulls something in a straight line. If you kick a ball, it moves forward. That's force doing its job. But torque is different. Torque doesn't push things forward or backward. It tries to rotate them. It's a twisting effect, not a straight push. Now here's the interesting part. Gravity is just a force. It pulls everything straight down. So why doesn't everything just drop straight down instead of tipping over? The answer is position. Gravity acts on the center of mass, not necessarily at the point where the object touches the ground. When that downward pull happens at a distance from the pivot point, it creates torque, and torque causes rotation. So the object doesn't just fall, it falls by turning. Think of it like trying to move a heavy cupboard that's stuck on the floor. If you push it straight from the center, it might not move at all, it just resists. But if you push from one side or at an angle, suddenly it starts to twist or turn. You didn't increase the force. You just changed how that force acts relative to the pivot point. That twisting effect is torque in action. So gravity isn't doing anything special or mysterious. It's still just pulling downward. But because of where and how it acts, it creates a rotation instead of simple downward motion. And once you really understand this difference, you start to see that the spinning top's behavior isn't about fighting gravity. It's about how rotation responds to that same twisting influence in a completely unexpected way. Now here's the moment where the whole story quietly changes direction. Up until now, it's very natural to keep asking, what is holding the top up? It feels like the right question because that's what our eyes are telling us. Something upright, something resisting gravity, something refusing to fall. But that question actually hides the real mystery instead of solving it. Because the truth is, nothing is holding it up in the way we imagine. Gravity is still pulling down. The table is still pushing up. Those forces haven't changed at all. So the better question is not about what is stopping the fall, but about what happens when the same torque we talked about acts on something that is already spinning. And that's the part most explanations rush through too quickly, even though it's the real turning point. A non-spinning object reacts to torque in a simple way. It starts rotating and falls over. But a spinning object is already in motion, already carrying angular momentum. So when torque tries to rotate it again, the response is no longer straightforward. It doesn't just tip down the way a still object does. Instead, it reacts in a completely different direction than what you expect. This shift in thinking is important. We are no longer talking about why doesn't it fall. We are now asking, how does a rotating system respond when something tries to twist it further? And that's where intuition starts to break and real physics begins to show something far more surprising. Now let's move away from the table for a moment and try something that feels almost unfair the first time you experience it. Imagine you're holding a bicycle wheel in your hands, not attached to anything, just the wheel with an axle through it. Someone gives it a strong spin so it's rotating fast. Now you hold it carefully by the axle, one hand on each side, and feel that steady, powerful motion trying to keep itself going. At first, everything feels normal. But then you try to do something simple. You try to tilt it to the left. And this is where your expectations completely break. Instead of the wheel just leaning left the way you pushed it, something strange happens. It doesn't respond in a straight, predictable way. It doesn't even resist in the normal sense. Instead, it moves in a direction that feels completely unrelated, almost like it reacts at a right angle to your push. You try left, it goes somewhere else. You try forward, it responds sideways. It feels like the wheel is refusing to obey your hands. And honestly, the first time you feel this, your brain just pauses for a second. It's a bit like playing a racing game with a broken controller where you turn left and the car goes right, but even more confusing because there's no obvious logic to it at all. Or like a steering system that has decided to interpret your inputs in a completely different language. You know what you want it to do, but the response is always slightly off, as if the system has its own hidden rulebook. That feeling confusion mixed with curiosity is exactly the point. Because nothing is actually wrong with the wheel, and nothing is wrong with your hands either. What you're feeling is the natural behavior of something that is already spinning when you try to change its direction. And once you see that strange 90-degree response clearly, the real question becomes even sharper. Why does rotation behave like that in the first place? To understand what's really going on, we need one simple idea, something that feels almost like stored rotation. When something is spinning, it doesn't just have motion in a casual sense, it carries a kind of built-in rotational memory. In physics, we call this angular momentum, but you can think of it as how strongly an object is committed to continuing its spin. Now, this stored rotation has two important parts. First is how much rotation it has. A heavy wheel spinning fast has a lot of it. A small, slow-spinning object has much less. So speed, mass, and how far the weight is spread out all matter. This is the magnitude, the strength of the rotation. Second is which direction that rotation is pointing. This might sound strange at first because rotation doesn't look like it has a direction, but in physics, we treat it like it does. We use a simple trick called the right-hand rule. If you curl the fingers of your right hand in the direction of spin, your thumb points in the direction of angular momentum. It gives rotation a direction in space, like an invisible arrow sticking out of the spinning object. A helpful way to picture this is to compare a slow fan and a fast fan. A slow fan turns lazily, easy to stop, easy to change. But a fast fan feels different. It resists change. If you try to slow it or tilt its motion, it pushes back in a strange way, as if it wants to preserve what it already has. That stubbornness is really angular momentum at work. So now we have something important. Spinning objects don't just rotate, they carry a directed quantity that resists change. And once torque enters the picture, it doesn't simply tip things anymore. It interacts with this stored rotation in a much more subtle way, and that's where things start to get really interesting. Now we reach the real heart of the whole idea, the rule that quietly controls everything we've seen so far. In physics, the relationship is surprisingly simple. Torque changes angular momentum. That's it. No hidden force, no extra ingredient. Just this connection between twisting and changing rotation. But here's the part that makes it truly powerful. When torque acts on a spinning object, it doesn't change everything at once. It changes the angular momentum only in the direction of the torque itself. Not randomly, not straight down, only in the direction it is being twisted. And this small detail is where all the strange behavior begins. Think about pushing a shopping cart. If you push it straight from behind, it moves forward nicely. But if you push it slightly from the side, the cart doesn't just speed up, it also starts to turn. Your push has two effects at the same time. Forward motion and a sideways change. The direction of your push decides how the motion shifts. Or imagine trying to steer a moving bicycle. If you apply force on the handlebar, the bike doesn't instantly jump sideways. Instead, it gently changes direction over time. The change doesn't happen opposite to your force. It happens in the direction you influence it. That's exactly what torque does to a spinning object. It doesn't destroy the spin. It doesn't stop it. It simply adds a small nudge to its angular momentum in a specific direction. And when something is already spinning strongly, even a small directional change can lead to a completely new path of motion. So now we're getting closer to the real mystery. We know torque is acting. We know angular momentum exists. The real question becomes, what happens when a strong, steady spin keeps getting tiny sideways nudges over and over again? That's where everything starts to shift from simple rotation into something far more surprising. Now we're finally at the point where everything clicks into place. We already know gravity is applying torque, trying to tip the spinning top over. So naturally, you would expect it to fall down just like a pencil. But something very different happens instead. The key is this. Torque is not pushing the top down in a direct way. It is constantly trying to change the direction of the top's stored rotation. But because the top is already spinning fast, it doesn't respond by simply tipping. Instead, the change shows up in a completely different direction sideways. So instead of the top collapsing forward into the table, its motion gets shifted to the side. And this is the strange part. The top is always falling, but it never falls in the same direction long enough to actually hit the ground. It keeps redirecting its fall in a smooth turning path. It's a bit like trying to push a moving bicycle from the side. Instead of the bike just stopping or tipping immediately, it gently curves. Your force doesn't simply end the motion, it changes its direction. Now imagine that happening continuously. Gravity keeps applying torque. The direction of the change keeps shifting. And instead of falling straight down, the top's axis slowly traces a circular path in space, like it's drawing a cone in the air. This slow, steady circular movement is what we call precession. But at its core, it's nothing more mysterious than falling that keeps getting redirected sideways again and again. So the top isn't defying gravity at all. It's actually obeying it very precisely, just in a way that makes the fall happen in a circle instead of a straight line. Let's make this part crystal clear, because this is where the magic really starts to look like something you can actually see and feel. What we are calling precession is simply this. Instead of the spinning object falling straight down, its axis slowly moves in a circle. That's it. The top is still under gravity, still being pulled down, but instead of collapsing in one direction, it keeps turning its fall around in a smooth loop. You can think of it as falling sideways continuously. Not stopping the fall, not reversing it, just constantly redirecting it so the fall never completes in one straight line. The result is a slow, graceful, circular motion of the spinning axis, almost like it is drawing an invisible cone in the air. A very easy way to picture this is a spinning coin on a table. At first it spins upright, fast and stable, but as it slows down, you start to notice something interesting. It doesn't just stop, it begins to wobble. The top edge starts circling, tracing a small loop before the coin finally gives up and falls flat. That wobble is a simple, everyday version of precession showing itself. Another example is a wobbling plate or tray when you try to balance it on your finger. If it's not perfectly still, instead of falling straight away, it often starts to circle around the support point. You can literally feel the center shifting in a loop before it eventually collapses. Again, it's the same idea of falling that keeps changing direction instead of going straight down. So now the picture becomes much clearer. The spinning top is not magically suspended in air. It is continuously falling, but the fall is being smoothly redirected into a circle. And that circular falling motion is exactly what keeps it looking stable for so long. Now, let's push this idea one step further, because this is where things start to feel almost counterintuitive, but in a very satisfying way. When something is spinning, it doesn't just have motion. It has angular momentum, a kind of stored rotation. And here's the key idea. The bigger this angular momentum is, the harder it becomes to change the direction of that rotation. So if a spinning object has a lot of angular momentum, it doesn't like being tipped or redirected easily. It resists change not by stopping the force, but by reacting in a slower, more controlled way. That's why fast spinning feels so stable. Think about riding a bicycle. When you ride slowly, the bike feels wobbly. A small turn of the handle can throw you off balance. But when you ride faster, everything suddenly feels smoother and more stable. The same tiny correction doesn't knock you over anymore. It just gently adjusts your path. The motion becomes harder to disturb because the system is committed to its direction. Or take a cricket ball spinning in the air. A fast spinning ball is harder to predict and doesn't react sharply to small air disturbances. But a slow tossed ball without spin is easy to mess up. It drifts, dips, and loses stability much faster. The spin gives it a kind of resistance to change, almost like it is holding its direction more firmly. So the deeper idea is simple but powerful. It's not that spinning creates stability out of nowhere. It's that a larger angular momentum makes the object harder to redirect. And when torque tries to change its direction, the response becomes slower and sideways instead of sudden and direct. And that's exactly why the faster the spin, the more stable the system appears, even though gravity is still doing the same job in the background. Now, if you watch a real spinning top carefully, you'll notice something interesting right at the beginning. It doesn't become perfectly stable instantly. Instead, it wobbles a little, almost like it's figuring itself out before settling into a smooth motion. This early wobbling is actually a natural part of the process. When you spin the top and release it, it doesn't start in the perfect balance for steady motion. There's a small mismatch in angle, speed, or release timing. So instead of going straight into smooth circular motion, it first reacts with a bit of up and down and side-to-side shaking. This is the system adjusting itself. A simple way to picture this is a glass of water that you've just picked up after shaking it. The water doesn't instantly become calm. It swirls, sloshes, and slowly settles down into a steady level surface. The energy inside needs a moment to spread out and stabilize. The spinning top behaves in a very similar way. It needs a short adjustment phase before it finds its steady rhythm. As it continues spinning, this wobbling slowly reduces. The motion becomes more controlled, and the top settles into smooth precession. In physics terms, this early shaky movement is called nutation, but you don't need to think of it as anything complicated. It's just the system finding balance after being disturbed at the start. And the important point is this. The wobble doesn't mean something is wrong. It's actually a normal part of how spinning objects stabilize. Once the excess shaking energy is settled, what remains is the clean, steady motion that keeps the top looking almost effortlessly balanced. Now here's where this idea stops being just a cool physics trick and starts becoming something you actually use in real life every day without even noticing. Take a bicycle first. At low speed, riding feels shaky and difficult because even a small tilt quickly turns into a fall. But as soon as you gain speed, the bike suddenly feels stable. The spinning wheels are carrying angular momentum, and that makes it harder for small disturbances to instantly tip the system over. Instead of falling immediately, the bike gently corrects itself, giving you time to balance. That's why learning to ride feels hard at first, and then suddenly becomes natural once speed enters the picture. Now think about your smartphone. Inside it, there's a tiny device called a gyroscope. It detects rotation and helps your phone understand orientation, whether you are holding it straight, rotating it, or tilting it. When you play games, rotate maps, or use AR filters, this sensor is quietly tracking angular motion using the same physics idea we've been talking about. Without it, your screen would feel completely confused every time you moved your hand. And it doesn't stop there. Navigation systems, especially in aircraft, drones, and rockets, rely heavily on gyroscopic stability. When GPS signals are weak or unavailable, these systems still need to know direction and orientation. Gyroscopes help maintain that sense of balance and direction using spinning motion and angular momentum, making sure the system doesn't lose track of where it's pointing. Even modern technology like drones uses this principle constantly. A drone doesn't stay stable just because of software. It stays stable because its internal sensors are constantly correcting tiny tilts and rotations using gyroscopic feedback. Without that, it would wobble and crash almost instantly. So what started as a spinning top on a table is actually the same idea behind bicycles, smartphones, drones, aircraft, and navigation systems. Different machines, same hidden principle, spinning motion, quietly keeping things stable in a very unstable world. Now let's go a little deeper, but in a very simple way, without turning this into heavy math or complicated theory. If you step back and look at everything we've discussed, there's a hidden idea running through all of it. Spinning tops, bicycles, planets, even tiny particles, they all follow the same rule. And that rule exists because the universe doesn't prefer one direction over another. In simple words, nature treats all directions equally. Up, down, left, right, none of them are special in the laws of physics. If you spin something in space and remove outside disturbances, it behaves the same no matter which way it's oriented. There is no favorite direction built into reality. And this simple fact has a very powerful consequence. Certain things must stay constant. In this case, the quantity related to rotation angular momentum doesn't just disappear or randomly change on its own. It is preserved because the laws themselves don't change when you rotate the system. So when you see a spinning top staying upright, it's not because the universe is helping it or fighting gravity in a special way. It's because the rules of physics are fair in every direction, and that fairness forces rotation to behave in a very specific, predictable way. This is also why the same idea shows up everywhere, from small toys on a table to the motion of planets in space. The system doesn't care about scale. It only follows symmetry. And from that symmetry, all the strange but beautiful behavior we've seen naturally appears. Now let's zoom out completely, from a spinning toy on a table to something much, much bigger. The Earth itself is basically a giant spinning top floating in space. It spins on its axis once every 24 hours, just like the tops we've been talking about. But here's where it gets really interesting. It doesn't spin perfectly still in one direction forever. It slowly wobbles. This slow wobble is called axis precession, and it happens because of the gravitational pull from the sun and the moon acting on the slight bulge of the Earth. Just like with a spinning top, this causes the Earth's spin axis to slowly trace a circular path in space instead of staying fixed. But here's the key detail. This movement is extremely slow. One full cycle takes about 26,000 years. That means the direction Earth is pointing in space is constantly shifting, but at a pace so slow that we don't notice it in daily life. Because of this, even the North Star is not permanent. Right now, we use Polaris as our guiding star, but it won't always be there. Over thousands of years, the Earth's axis slowly points in different directions, meaning different stars take turns becoming the North Star. In the distant future, Vega will take that role, and long before that, ancient civilizations actually saw different stars in the sky as their pole star. So what looks like a simple spinning top on a table is actually the same physics written across the scale of planets and time itself. Now let's shrink the scale all the way down again from planets to something unbelievably small. Inside atoms there are particles like electrons. And surprisingly, electrons also have something like spin. But don't imagine them as tiny balls physically rotating in space. That idea actually leads you in the wrong direction. There is nothing spinning like a mini planet. Instead, spin here is more like an internal property, a built-in kind of rotation that nature simply gives them. What makes it even stranger is this. This spin is not optional. Every electron has it. It's always there, fixed in strength, as if the universe has decided that certain particles must carry this hidden form of rotation as part of their identity. And when you try to measure it, you don't get smooth results like in the everyday world. You only get specific outcomes, like the system is choosing between a few allowed states instead of anything in between. So at this level, rotation is no longer something you see like a spinning wheel. It becomes something deeper, almost like nature has built rotation directly into the fabric of reality itself. And that's the amazing connection. From spinning tops on a table, to the motion of planets, all the way down to electrons inside atoms, the same idea of rotation quietly keeps appearing again and again in different forms. So after everything we've seen, let's bring it all together and add one more layer that makes the picture even clearer. A spinning object is not fighting gravity. It's not being secretly held up by some invisible force, and it's not escaping the rules of physics. Gravity is still there, pulling it down exactly the same way as before, with the same strength, at every moment. What spinning actually does is change how that downward pull expresses itself. Instead of producing a simple straight collapse like a pencil falling, the effect gets continuously redirected because the object already has strong angular momentum. So rather than tipping directly into the ground, the motion keeps turning sideways again and again. This is why the top looks so stable. It is not refusing to fall, it is constantly falling. But the direction of that fall keeps rotating. The result is a smooth circular motion instead of a straight drop. That circular motion is what we call precession, and it is basically the system delaying the fall by spreading it out in a loop. But there's another important detail. This stability depends heavily on how fast it spins. A fast spinning top has large angular momentum, which makes it harder for gravity's torque to quickly change its direction. That's why it looks steady and calm. As it slows down, the angular momentum decreases, the redirection weakens, and suddenly the wobble increases until it finally collapses. So what you're really watching is a balance between two things: gravity trying to tip it over, and angular momentum spreading that tipping into a sideways motion. And that's the beautiful conclusion. Nothing in the system is stopping the fall. The fall is still happening. It's just being continuously reshaped into motion that circles instead of crashes. It was never standing still. It was always falling, just in a circle, slowly revealing how motion itself can hide what gravity is truly doing. Now here's something I really want you to try for yourself, because this is one of those ideas that becomes much more powerful when you actually see it with your own eyes. Find anything that can spin: a coin, a bottle cap, a small wheel, or even a simple toy top. Spin it and just observe it carefully. Watch how it behaves when it's fast, how it slowly starts to wobble, and how its motion changes as it loses speed. Then gently nudge it and notice what direction it reacts in. Don't rush it, just watch like you're seeing it for the first time. Because this is the real way physics becomes real. Not through formulas first, but through observation. When you start paying attention, you begin to notice patterns that were always there but hidden in plain sight. Motion starts to make sense in a deeper way, not as random movement, but as something structured and predictable. And once you see that, you'll start recognizing this same idea everywhere: on bicycles, in machines, even in planets moving through space. It all connects back to the same simple principle of rotation and change. So don't just take the explanation, test it. Observe it. Question it. I am Richard Feynman, and this is Feynman Rebirth.